Okay. So this afternoon session, we have Sang-hyun Kim, who is also making slow progress in his course.
Okay, thank you very much for the invitation and the introduction. So today I'd like to talk about the last part of the theorem. So as I said, as was said, I'm going slower than planned, but hopefully the last part is can be delivered as planned. So it seems like everyone is starting with confessing the missing references. I'm giving another related work. It is still unpublished, but due to Mahan and Wolf. So we have to, well, the theorem is that, let me explain the term right after stating the theorem, that there exists C, so what is it? For all epsilon positive, there exists C1 plus epsilon differentially rigid, finitely generated group. So let me explain what this means. So differential rigidity is due to advantages, stating that so a group which is very smooth of, say, circle. You can also say the same thing for the interval, but is called differentially rigid. Is CR differentially rigid if any embedding into if R. So presumably the regularity has decreased, but the source of this decreasing of regularity is only by conjugation. So if for all embedding of gamma into diff R, there exists some diff R such that rho is nothing more than conjugation of inclusion by omega. So omega inclusion and omega inverse. So you don't have any other way of embedding gamma into lower regularity other than conjugation by CR map. So Gis proved that surface group satisfies this C3 differential rigidity. And then Mahan and Wolf considered some combination of the cipher fiber space group that I explained, and also Baumslag solitary group. And then they proved that there exists C1 plus epsilon differentially rigid group. So why does it matter to our purpose? Well, it's now easy. It then becomes an easy corollary. That so let me just explain. So assuming the theorem, I say, let's name it, say gamma 1 plus epsilon. And then you consider, say, peak diffeomorphism, which is CR, R is any real number, which is never in the higher regularity. So this is easy to build by integration. Then, and consider this group, gamma, R, and F, which is subgroup of if R plus S1 by definition. Also, right, yeah. Let's name it as R. R is any real number, at least one. Same thing, I just rephrased it. Then this group never embeds into diff S for S any larger than R. Because if there is an embedding of gamma R of F into if S plus S1, S larger than R, Okay. Then this gamma R part must be a consequence of W conjugation for some CR. There exists, and there exists W in DFR such that so rho G is nothing more than G W inverse. But this contradicts that F can never be conjugated into DFS by CR map. Is critical regularity R. So you can never increase the regularity. Okay. So, well, but this doesn't really have anything to do with today's talk, or so this is alternative approach to find groups of certain critical regularity. So today I'd like to talk about something called slow progress lemma. So, yes.
So, gamma R comma F, say under suitable assumptions on F, can you ensure that this group generated by these is the product of certain group with gamma R?
No, I don't think so. So, I mean, so in this approach, this differential rigidity is then used almost as a black box. So we have very little information about the kernel of the map if there's a homomorphism into DFS.
Yeah, so, right. What do you expect?
Yeah, it should be infinitely represented. So yeah, it doesn't give much information about. So it does information about this the kernel. Yeah.
Was in the definition where you talk about CR differentially rigid.
Yep.
I think you mentioned this, but you can replace infinity in this differently S1 by some regularity. It could be some S0 regularity, and then the same thing goes for lower regularity.
You mean tweaking the definition of not necessarily requiring diff infinity? Yeah, but that should be fine for the purpose of this theorem. So yeah, as long as infinity is larger than R. Yeah. Right. So, but today I'd like to give a different proof. I mean, our original proof about this construction of groups of critical regularity. And so the key part, I'll actually explain the heart of the proof. What is the information that we exploit. So let me give some discussion on diffeomorphisms of disjoint with disjoint support, which I did a little bit in 2 days ago. So one thing, the first thing is actually not about disjoint support, but rather the opposite, non-disjoint support. So if you have two maps of M1, where by M1 we always mean compact one manifold, compact connected one manifold, like in other words, circular interval. And suppose you have C0 map. And if, say, so this is given, and for I equal 1, 2, 3, there are intervals, Ji, they might be overlapping, it doesn't matter. And say some point is mapped all the way to the left by F, and some point is fixed on the right, and G is doing exactly the opposite. All the way to the right, and G is fixing some point G. So F and G are not even assumed to be homeomorphism, but at least they are doing this. And JIs are allowed to overlap even. And finally, but at least the lengths are going to 0. Then the conclusion is that F or G is not C1. So this is one instance of many results regarding relating topological dynamics to regularity. So certain topological configuration, purely topological configuration, can never happen in C1 regularity. So does the statement of the lemma make sense? Right? So you have two maps, and there are many infinitely many intervals doing this thing. Some point is all the way to the left, some point is fixed by F, and G is doing the opposite. So let me give you a proof of this, because this is very simple. It's actually a mean value theorem. So let's name it, say, name the points xi, yi, zi. And let's name the intervals, or length of intervals, left part and right part. And that's it. Okay. And then we can apply the mean value theorem. So fzi minus fxi minus zi minus x. Okay. In other words, this is 1 plus xi minus fxi, because x, right, over zi minus x, right, because zi is fixed. Then this is at least 1 plus zi minus xi is smaller than ri. And denominator is precisely, numerator is precisely li. Okay. And similarly, you can believe that g xi minus gyi over xi minus yi is 1 plus ri over li. Everything is symmetric, the left and right. And so this is f prime of ui for some ui. This is g prime of vi for some vi. And everything is compact. compact. So ui, vi converges to up to subsequence, some point x naught. And if ui and vi's are converging, then this yi, xi, zi, everything converge, because the lengths are going to 0. So every point for some subsequence converges to some point x naught. And because x naught is the limit point of fixed points, prime is 1. Because x naught is accumulated by fixed points. So mean value theorem, there are accumulated points of prime 1s. So they are prime 1. But on the other hand, their multiplication is at least 4. So we have a large margin of being false. Okay. So this is a contradiction, assuming f prime and g prime exists. So I forgot to write down assumption. Assume C1. Assume f and g are C1, and you can apply mean value theorem, but they converge to some point with derivative 1, although prime multiplications are larger than or equal to 4. So this is right, because zi converges to x naught, because the lengths are going to 0. So here's x naught, and say z1 fixed, z2 fixed, z3 fixed. So accumulated x naught. Therefore, somewhere in between, there is a point with f prime equals 1. Because mean value theorems, if this is fixed, then something is prime 1. In between here, f prime equals 1 for some point, and so forth. So it is accumulation points of derivative 1 points. So this is a very simple, but it's a starting point. So you can relate topological configuration to regularity. And also, this kind of phenomena happens very often if you have a so-called strong crossing. So say F and G are, say, homeomorphisms. For example, I'm writing just example. And say you have a interval from, did I introduce tilde notation? So F tilde is more commonly written as support F. Actually, yeah, we are the only one using tilde notation, which is a complement of the fixed point set. Sometimes you look at the books written by geometers or analysts, support usually means closure of the support, closure of the set. But in our talk, this is just complement of fixed point set, so it's open set. So tilde. So if you pick JF and JG from F tilde and G tilde, then, so, and such that you have this configuration. And not just that, suppose F and G are fast enough. In other words, suppose some point is moved out of the intersection by F, and say some points are moved out of the intersection by G. So assume this scenario happened. Then you see the configuration of JI, because this point, right-hand point of JF is by definition fixed by F, and this left-hand point of JG is fixed by G. So this is precisely the configuration of JI written above. So the message of these two jumps lemma is F and G are C1, then this configuration cannot happen infinitely many times. In other words, there may be many crossings, but the crossings should be weak. It cannot be strong enough so that some points are moved out of the intersections. So that's the another interpretation of ABT lemma, two jumps lemma, and ABT lemma is a consequence. Okay, so what is it? So if you have ABT in diff one of compact one manifolds, such that A tilde and B tilde are disjoint, then actually there are two claims. So first claim is that for some concrete element U0, I can even write this down. This is a conjugation by T, B perturbation of B conjugation, and A. For U, the closure, CL means closure for me, of U0 tilde is contained in open support of the rest. So this is part, although, well, so the part that we really care is part two. Actually, part one is sometimes used. So for some concrete element, this is compactly contained in the support of everything. And then you deduce that ABT can never be isomorphic to Z2 star Z, although A and B are disjoint. So I can explain why number one implies number two. So say proof of number one implies number two would go as follows. So here's the situation. Situation is that this U0 tilde support of U is could have like may have infinitely many connected components, doesn't matter, but at least the whole thing is compactly contained in the support of everything. So here say A support, something like this. This is support of A. And support of B is disjoint. Support of B is disjoint, something like this. And support of T fills in the gaps. Say T tilde. Let's make it simple. It's two. Oops. It's too complicated. So I'll just make it simpler. So A is feeling this, B is this much, and T is this much. And here's U. Okay. So something like this. Of course, we are not assuming that the support of ABT, this thing is connected. We are not assuming that this is connected. So maybe there is another picture, completely disjoint picture here, completely disjoint picture, or finitely many, because U0 tilde is compact. Then in this very specific example, you see that if you A to the very high power and T to the very high power, B to the very high power, and say T to the another high power and A to the very high power, will move U0 tilde off itself. In this very specific example, right? Because U0 tilde is something like this. Now apply very high power of A, then the infimum will be passed through something like this so that it belongs to support of T and move into B and move into T and move into the support of A. So infimum of U0 tilde after applying very high powers of these elements will be larger than the supremum of U0 tilde. Yes. Right. So that's the whole point, right? I'm proving 1 through 2, so assuming 1. So closure of U0 tilde is contained in this open set. So if you look at so let's make it simpler by assuming U0 tilde is a single interval. Okay. Then infimum will be in the interior of support of A in this picture. Well, support is open. Right. So that's the point, right? Compact set is contained in this open set. So infimum is like passed into the next supporting interval, next supporting interval, next supporting interval, and next supporting interval. Apply very high power. Then this will be the picture of support this image. So we have so let's call this word as W. Then we have a kernel element U0, W, U0, W inverse is trivial. If there is only one connected component of the right-hand side. If there are several, then you apply this successive conjugation. So in general, like you define it as U1 and do the same thing, U1 and then W1, one inverse as U2, and so forth. And then eventually it will converge, it will land at a trivial element. And this is a certificate that the group is not Z2 star Z, because Z2 star Z cannot have this kind of kernel. So this proves part 2 from part 1. And for part 1, I don't have time to go over the detail of the proof, but basically taking us enoughly many commutators cuts out supports at the accumulated at the endpoints of the supporting intervals and apply this 2 jumps lemma to show that you have only to worry about finitely many intervals and then cut out things like. So one useful and very simple observation, general fact is whenever you have 2 elements, say G and H, and you take a support and closure, then this is intuitively clear. So you have only to worry about open supports and then closure of intersection only. So this is the general approach. Whenever you're taking the closure of the support of commutator, then the endpoints are basically cut out except for when 2 supports intersect. And then you will have to worry about closure of that intersection. Okay. Right, so we have these 2 lemmas, 2 jumps lemma and ABT lemma. And then you can finally state slow progress lemma. So, see. It's written above, so I'll just write down SLP. So slow progress lemma is relating orbit behavior to regularity. So our strategy is, well, our theorem is basically about group structure, but group is somehow related to orbit behavior, and orbit behavior will be related to regularity. So to relate that, let me make the following definition. So suppose you have a subset, say homeomorphism, in the homeomorphism group, then, and say K is subset. We only care when K is an interval anyway. Then you can define covering length. Covering length with respect to V of K as the minimal number of intervals from the support to cover K. The minimum number of L such that K is contained in J1 through JL, where JI is I0V. So there is some, whenever you have a compact set, you want to cover it. So if K is given, you want to cover it by supporting intervals of the homeomorphisms that you have, right? F and G and so forth. Okay. So this is certain combinatorial quantity or topological quantity, if you want to call it that way. And then we have a connection between this orbit behavior and group theory in the following lemma or observation. So first of all, if you have, say, some homeomorphism, then we can define, well, this is purely group theoretic, so it doesn't have anything to do with homeomorphism, but you can talk about syllable length with respect to V. So whenever you have a group element, so what is it? So let's just make it purely abstract. It's easier to understand. So if G is inside a group generated by S, then you can talk about its syllable length. So this is minimum of L such that G can be written as S1 to the power to SL to the power. So this is a well-known quantity, so purely group theoretic. Then lemma or observation. A pi 0 V means pi 0 V tilde. Sorry, thank you. Right, so connected components, so open intervals inside this open support. Then the observation is that right, so in the left setting on the left hand side, covering length with respect to V of K is same as the minimum syllable length that you require, such that G, with respect to V, of course, such that GK is made of itself. So we always assume K is interval when you talk about covering length, although you can talk about, like, you can define covering length for non-intervals, but we only care about the case that K is interval. So this is the connection between group theory, group theoretic quantity, and this topological quantity. So why is it? So the picture is already given there. So proof sketch is that, well, so here's K, and suppose it was covered by, say, 3 supporting intervals. Say, here's A, here's a B, and here's C, where A, B, C belongs to the generating set. Then you can easily find large integers, positive or negative, such as AP, EQ, CR of K will be disjoint from K in this example. So in general, if it is covered by L intervals, then you can make it off itself by applying syllable length L group element and so forth. So this is clear, and the opposite direction is also clear. Now we want to relate this topological quantity to some analytical quantity. We want to measure the distance. So this is just counting the number of intervals. Now we want to measure the distance. So that is the place where the regularity becomes matter. So now we can define slow progress lemma. So I'll just erase the proof because this is just very simple picture. So slow lemma can be stated as follows. So suppose you have some finite set inside C, say S diffeomorphism group of interval. S is real number at least 1. And suppose you have a sequence of vertices. Okay. You can choose anything. It doesn't have to be uniform or anything, just any sequence. And consider any point on the interval. And consider powers, which is not exceeding I to the S minus 1. Okay. So up to multiplicative constant, not exceeding I to the S minus 1. These are the hypotheses. Then you can try to compute. Well, let's just define Wi for the ease of writing. This is apply n1th power, n2th power, n2nd power, and nth power. That is the element in the group generated by V. And if you measure the covering distance, did I define covering distance? Covering length of X and V1 and 1, or I define Wi. Wi, Xi. Of course, if Wix, if Wix is smaller, then just switch the order, okay? And this covering length, so it makes some progress, V1 to the A1, V to the N2, Vi to the Ni. Okay, so it may or may not move X further and further. It may move back, but it may progress, it may not, it may revert. But anyway, the progress cannot be small. That is the content. So if you take lim sup, then it is less than 1 minus epsilon, or strictly less than 1. That's it. Yeah. So that is the content of the lemma. So, right, the whole point is about this power. So measurement of the power. If the power is not too large, sometimes applying V1, N1, V2, N2, V3, N3, and so forth. So X may move to the right, and then left, right, left, doesn't matter. But it cannot progress too much at the linear scale. So that is right. That is connecting this regularity S, or this I to the S minus 1, to this orbit counting or this interval counting problem. So Let's see. So I'm planning to two things. One thing is how this implies the main theorem, and the other is what are the idea relevant to the proof of slow progress lemma. So let me probably do the former thing first to prove the theorem. So let me state the theorem again. So theorem B. I said this implies theorem A, that for all real number, there is some representation of some fixed group, G star, into if R plus I. The precise form of G star doesn't really matter for our purpose, but it's some finitely generated group. I'll just give the definition later. Such that whatever larger regularity you consider and whatever representation you consider, the kernel will be larger. So that is the theorem. Here, G star is group generated by some finite set. And concretely, this is a Z cross Baum-Sulak solitary group F2, whose generators are written as centralizer A and E, where A conjugates E to E squared, and BD. But as I said, the precise presentation doesn't really matter for the purpose of this theorem. Yes.
Can you control anything about how WIS takes further or from previous which is the same, is telling us that
No, apparently it doesn't have anything to do with the lengths of the intervals. It's just related to the number of intervals. Typically, the lengths of the supporting intervals are converging to 0. And they are very small, they may be just accumulated somewhere even. But we are just counting the numbers of the supporting intervals. And then, right, so one intuitive interpretation is that, like, so you're starting from X and W1X and say W2X and then so forth. But if you count, so if you have a jump and another jump and another jump and so forth. So after 100 jumps, maybe you have made 100, you have passed through 100 different intervals. But this is saying that there's more efficient way, sublinear way of covering the interval from X to W100. Maybe like you only need 70 of them, like only 70 intervals and cover. You don't need the whole 100 intervals. Okay, so right. Yes. Right, yeah, right, precisely, right. Because right, in each progress, either progress is not made, but even if progress is made, that is due to single interval. So lim sub is m most 1 anyway. Right. Yeah. Okay, so and as I said, G star is some finitely generated, finitely presented group having like these kind of things. V denotes the generating set of V, or A, B, C, D, E. Okay. You can just forget the presentation. And so let me briefly explain how slow progress lemma implies theorem B. So how do we start? So we have to build a representation. So first of all, to build a representation, we have to specify many things. So first of all, we'll specify the length of the interval as 1 over I log squared I, or up to some additive constant, because you don't, well, this is fine. This is just fine. Length is 1 over I log I squared. I is at least 2, say. And we will also specify Ni as the 1 over Li to the R minus 1. So in other words, this is something like, this is certainly strictly less than I to the S minus 1. Okay, for all S. We are in the process of building VR. But whatever S you consider, I to the S minus 1 will be strictly larger than 1 over Li to the R minus 1. So of course you want to take a floor or ceiling, doesn't really matter. Now we want to engineer EI. So, right. So we will engineer. I cannot give a detail, but I'll just say engineer ER, so define VR such that some of the following conditions hold. So first of all, in pictures, that will look something like this. So some elements are acting here, A, B, C, D, E acting here with some finite configuration of supporting intervals. And then you will have some segment supporting interval of A and supporting interval of B and A again and B again infinitely many times. So that the length is say L1. It is just, yeah. Length is L2, L3, L4, so that everything is compact. And to do it exactly the opposite on the other side. A, exactly symmetric. And then the direction of travel is moving away from the center. Okay. And moreover, oh, you mean the length is this thing. I didn't explain, but this is just finite configuration of supporting intervals by A, B, C, D, E. So I'll explain something slightly more in part 2. But this is some group action of A, B, C, D, E. More precisely, like A cannot intersect. So the end point, I can write a little more. So here's E, here's C, and really some A, B, C, D, A, B, D, something like this. A, B, D, E, A, B, E, and A and C commutes. So sorry, C and E, C, something like this. Yeah, C, D. Something like, so that like A supporting interval and B C supporting interval do not intersect, but probably I made the picture just worse. So it is some group action of ABCD, group action ABCD, so that certain minimality condition holds. So they act sufficiently dense orbits. And a little bit more being said here, so that supporting interval of U0, the core element, universally compactly supported element, with respect to this, the very AB right? A, B, with respect to A, B, and D. Yeah. Or A applying to A, C, and D, something like this. So there is some universally compactly supported element U0 tilde and its closure, okay, let's call it as K, is connected interval. So this is the second requirement. So there is very concrete element so that this is universally compactly supported, but this is a single interval rather than empty set or several intervals with respect to phi. And also, so these are right. So I will even define W for VI. So WI that we are considering will be basically A to the N1, B to the N2, A to the N3, and so forth. So that ith Ni, A or B. So this is the very group element. And the third requirement is that such that phi R Wi apply to K. And if you compute covering length with respect to phi image of V, then this will be scale of 2i. So this requires a few explanation. So first of all, how is this possible? That means that if you move along, and then K will be something like this. It will be something like this. And then you are progressing by A to the N1, B to the N2, A to the N3, P to the N4, and so forth. And on left-hand side also, A to the power, B to the power, A to the power, and B to the power. So if you apply Wi in the representation phi R, the length, this covering length will grow like 2i on both sides. But you might wonder why this is not violating slow progress lemma. Well, it's because of the regularity. The regularity is only TIFR. Okay. We are engineering phi R. We are engineering phi R. As I said, phi R will be from G star to TIFR. But still, it is larger than I to the R minus 1. So the slow progress lemma's hypothesis was that the thing is I to the less than the regularity minus 1. In this case, it is the regularity is R in the construction of phi R. Therefore, we may or may not, but we can actually make the covering length to grow like 2i. And moreover, these things, they are infinite chain, and infinite chains are strongly crossed. Strongly crossed. So that you can make a jump on each power. So you might also wonder why this doesn't violate the two jumps lemma that we mentioned. Two jumps lemma mentioned that if you have two diffeomorphisms and you have a chain of supporting intervals, they are mostly weakly crossed, except for finitely many exceptions. But this doesn't violate the two jumps lemma either, because in two jumps lemma, you fix two diffeomorphisms. Here, diffeomorphisms are changing. A to the power, B to the power, A to the power, B to the power, larger and larger power. So it is possible that you can make these chains strongly crossed so that some points are jumped and jumped and jumped and jumped without exceptions. So by ABT lemma, if you do not consider powers, then it is never possible. You cannot increase it. But because powers are large, so you can make constant jumps. Okay. So that is the setup. So after some single variable calculus exercises, you can build this. Now consider any. Now consider any S larger than R, and consider any representation P of G star. Into if S plus I. And we want to find some kernel element which stays non-trivial under phi R. So that's the whole point. So how do we do that? So consider now psi of this universally compactly supported element, U0. Tilde closure. Let's name it as K prime. So this will be compactly supported in the union of the supports of the generators. So that is what we already know from ABT lemma. So of course, it might be just like many disjoint compact intervals, or even like Cantor set, or it may have many connected components. It doesn't matter. So I'll just draw K prime, something like this. Here's K prime. Okay. But by slow progress lemma, we know an upper bound for the growth of the covering length of this guy. The covering length of psi application of Wi to K prime, because you consider supremum and infimum separately, still covering length will be much smaller than 2i for all I sufficiently large. So that is the content of the slow progress lemma. For each point, it may make progress, but it is less than I. It may make progress, but it is less than I. So covering length is very small. So what is the situation in psi representation? In psi representation, so here's psi Wi of K prime. Covering length is small. Therefore, by the lemma that I stated, you can make it off itself with small energy. In other words, there exists some H with syllable length small. Syllable length with respect to V is much smaller than 2i, such that they are disjoint. Psi H psi Wi K prime. So this is possible. And this is really the connection between psi and phi. Otherwise, it seems like they are two different structures. Phi and psi have nothing really in common, other than it shares the domain group. And this measurement of syllable length is the only common feature that psi and phi can exploit. So this is really the connection. Other than that, phi and psi have really nothing to do with each other. Then looking at this H, you look at the phi picture. In the phi picture, here's K and here's phi Wi of K. And the point is that because covering length is so large, H is not enough to make it off itself. So phi of H Wi K will look something like this. Of course, you might have some worry that what if they precisely coincide, but we will not worry about it because there is a remedy for that by adding just a single Moore generator. So they will look like a chain in general. Then what do we have? Well, because of this disjointness, we have commuting relations. Psi Wi of, so psi Wi U0 Wi inverse, because K prime is support of U0, will commute with H Wi U0 Wi inverse H inverse. But because of this intersection, phi can never do that. So for that, I owe you a bit more explanation, but I'll just write it down first. And never be one. Okay. So let me explain a little bit more about this part. But in general, like if you make a chain, they will never commute. Okay. Actually, so I'll explain a little bit more about this. But first part is clear, right? Because disjoint support will give you commuting. And then this is the case when support of psi is connected. Then you have taken care of all the possible kernel elements coming from U0. You're done. If you have like psi, support psi is not connected, then you just apply the same argument of using commutators and just take care of one by one. Okay. So this is the end of the proof except this star. So let me explain a little bit more about that. So that is suppose Poppel's lemma. Actually, it's a variation. So she didn't state this her lemma in this form. The variation is that if F and G are C1 diffeomorphism of compact one manifolds, and they commute, and you pick a supporting interval of F and G respectively, then JF and I'm sorry, it should be C2 or JF JG equals empty. So actually it's different from Poppel's lemma. Poppel's lemma is some statement about C1 regularity, but it's something closely related to Poppel's lemma. Yes. S is greater than R. Right. So that's where slow progress lemma is applied. So psi is diff into diff S, and Ni is not large enough. In our definition, Ni is something like I to the R minus 1 log 2 R minus 1. So this is strictly less than I to the S minus 1. So you can apply slow progress lemma for psi representation. And for phi representation, we engineer that slow progress lemma's conclusion is violated. And we can do that because R is smaller than S. Because like this thing is strictly larger than I to the R minus 1. So we can without violating slow progress lemma, we can build phi R. Well, I didn't give you construction, but you can just believe that you can do that. Okay. And then so this is it. So yeah, I really should call this as a Helder-Poppel lemma. Helder-Poppel theory. Well, actually, yeah. All right. So Poppel's lemma is like C1 plus Lipschitz, but it's about the same thing. But anyway, so maybe there's some disagreement on naming this lemma, but this is a fact that you can prove that you have C2 diffeomorphisms, then the two in support intervals will coincide or disjoint. In other words, this never happens. So they commute. So there should be some repeating peak pattern, but this will never happen in C2. In C2 minus epsilon, this is possible. That is so-called Ziboi example or Pixton Ziboi example. But in C2 picture, this will never happen if you already know that F and G commute. So using this, you see that so they have not enough displacement power, but like this thing is not possible. And so they say this is K1, K2, and you cannot have like this thing or something like that because they commute. if they commute. If this were trivial, then these two things must be coinciding or disjoint. But disjoint is not possible because we don't have enough power, H, syllable length. And coinciding, I didn't explain, but you can kind of avoid it by adding just single mode generator. So that's the end of the proof. Yes. Here, oh, right. So that's also a very good point, right? So this is about C2, or at most C1 plus bounded variation. But that is not true for C1. But this is like maybe less than 2. So what's going on? Well, the thing is that for phi, we engineer that it is in diff R plus interval and diff infinity of open interval. So phi, yeah, that is something that I forgot to mention. So phi is engineered so that it is smooth inside. And this K is compact, so everything is happening inside. Therefore, you can just restrict the domain and see this violates Koppel's lemma. Yeah, actually, that is also an important point. So yeah, so this is basically like, you can summarize everything to this single line. So Y is just completely different, phi and psi related. Well, so this is just single point that phi and psi are related. There is a group quantity syllable length, and that's all. And other than that, they are not related at all. They behave completely independently. So for the remaining 10 minutes, I'll just give a brief summary of the proof of slow progress lemma. So what should I do? First of all, let's demystify this lim sup. This is not really anything mysterious. So lemma 1 is that. So if you have a lazy walk, in Z, in the sense that, well, so bi minus bi plus 1 is at most 1 and is integer walk. Okay? Then lim sup of dii is nothing more than the upper density of indices that are making new progress. dp is larger than max di. So this is elementary to check. This is almost definition, lim sup. So the left-hand side is slightly demystified. So you're just counting upper density of new progresses when you're applying V1 to the N1, V to the N2, V3 to the N3. When are you making new progress in terms of covering length? And so another thing, now this kind of density, there's a very well-known fact that if you have some set, and if 1 over P is finite, then the natural density is 0. Okay, so this is something that you can prove too, right? So if you have a positive density, then sum of the 1 over P will be positive. And now we want to somehow relate this orbit counting to the length counting. So let me make a definition first. So this is the really last definition that I'll be making. So suppose you have a map, homeomorphism acting on an interval. Interval is delta fast or delta expensive where delta is positive integer. This delta is not nearest delta, so this is fixed. You cannot increase it, but delta expansive if and only if the supremum of displacement compared to its distance to the endpoints. So x or fx measure distance to the boundary is delta. So this is so you might sometimes you consider the supremum of displacement divided by length interval, but that is not enough for us. We have to consider the distances to the endpoint. So this is really measuring 4 different distances: x to the a, x to the b, where j is a, b, and fx to the a, fx to the b. So to apply some kind of mean value theorem, we are giving a condition that delta expansive means it is at least, the supremum is at least 10 centimeters. Then these things can be combined to prove that, so let's call this called P as such a set that we want to measure the upper density. So this is the integer which is making new progresses. So covering length of x and wpx is a new progress. Okay, and we have only to give an upper bound for P, or just show that upper density of P is strictly smaller than 1. It cannot be everything. So the third lemma or claim is that, so let's call this P delta. Delta is any positive integer, can be extremely small, which is subset of P, such that Vp to the NP at Jp is delta expansive. So you just collect just count the number of intervals on which this pth term, pth syllable is acting fast enough, delta expansive. Then the density is 0. So this is, so lemma 3 is, probably I'll just take lemma 3 and just wave my hands and that will be the end for today. Di, right, Di is right. So Di is covering length of, yeah. So I often consider this distance, so I put this parenthesis, but it really should be this compact interval, right? Yeah. So I'll just explain why this is true. And then once this is established, then you see that, like, probabilistically, the progress in terms of the ratio of the interval length and the progress are very, very small. Delta can be taken as 1/billion or 1/billion times billion and so forth. So it's very small. So the progress will be, even if you raise to high power, the progress will be smaller and smaller and smaller. Therefore, you have just not enough power to make linear progress, and you just conclude. So why is lemma 3 true? So proof sketch. Right. So sometimes I in one instance I wrote sketchy proof, and that seems to mean something completely different. So this this is a proof of sketch. No, sketch of proof. Right. Not sketchy proof. Right. So what is how do we measure such a density? Well, so, right. So first of all, suppose for some P, Vp to the NP is delta expansive for some P. So P is in P. Then you can easily prove that onto JP. VP restricted to JP. Did I define JP? JP is just supporting interval that you encounter in pith terms. So you have a certain JP and say VP is acting on pith interval. You're just assuming that you're making linear progress. So assuming that VP is acting on JP, because P must, in each of P, you should make a new progress. So it should be more precisely, JP is by definition WP minus on X and WP of X. I should have defined concretely. So this is definition of JP. JP is just pith progress because you have to make a new progress. So this is pith progress, is JP. And VP to the MP is acting here. And high power is delta expansive, then itself is a logarithm over NP expansive. You don't have to worry too much about the numerator, but you can kind of believe that it is 1 over NP expansive because, yes. JP is by definition WP minus 1X and WPX because you have to make a progress at pith time. Yep. And then WVP is expensive, but on the other hand, using integral version of Taylor series, you see that VPX minus X is something like some point to the X, some point to the second variable, some point and some point xk minus 1 to the some point, say t, f k t. Say integral. Okay. So, well, this is also assuming something else that I didn't really care. Assuming, say these points, there exists some xi such that ith derivative of xi is ftp. Ith derivative of xi is same as identity derivative. Well, I should be this, yeah, right, same I. So for example, this x0 is fixed point, x1 is the point that prime is 1, x2 is the point that 2 prime is 0, x3 is the point that 3 prime is 0, and so forth. But you can always require that, which I didn't explain, but by slightly increasing JP, you can always require that there are some points such that ith derivative is same as identity's ith derivative. Then this Taylor series holds, and even more is true. So this is same as VP to the xk, where S is k plus tau. The regularity is k plus tau. So this is the point where analytic condition is used. Therefore, this is less than x minus x0 times the length to the k minus 1 times VP to the k to the tau Herder-Norm times JP to the tau. This is the definition of Herder continuity. Herder-Norm times length to the tau is the integrand. Therefore, this NP expansive constant is you divide BPX minus X minus X naught. So this is JP to the S minus. Because K plus tau. But what was our assumption? NP was at most I to the S minus 1. So this is I to the S minus 1 or P to the S minus 1. So 1 over P in T P delta is less than 1 over JP, but everything is compact, so this is finite. So this proves that density of P delta is 0. Okay. I went over 2 minutes. So I think this is the place that I can stop. So right, and then I'll just say that this probabilistic counting of progresses will give you the upper density bounded away from 1. Okay, I'll stop here. Thank you. Yes.
Because of the bounce back.
Right. So it is hidden. It is due to using the result. Actually, that's very good point. Something that I wanted to mention, but I couldn't. So it is due to Bonatti, Monteverde, Navas, and Rivas. In 17, they proved many things, but among them is that any representation of BS12, which is generated by Z cross BS12, AES cross C into diff1, you have a disjoint support, rho C and rho E is disjoint. And using this, so this is a seed. They are always disjoint. Therefore, actually that is a good point. So U0 in our case will be so C and some conjugation, a B inverse. Actually, E to B, E to minus B, and then C to B and C. Right. So this is the definition that we take, because C and E are sorry. C to the B and E to the B are always disjoint, whatever representation you take. Whatever representation you take, C support and E support are always disjoint. So to utilize the ABT lemma, you have C and E here, and you perturb by the other element and perturb by C. Then this will, so then whatever representation you consider of BS12 cross Z RZ into diff1, the supporting interval of U0 will be compactly contained. So this is really the seed. And using this seed, we conjugate and commutate and just generate many other elements. Thank you. And the proof of Bonatti, Monteverde, Navas, Rivas is basically that the action of Baumstruck-Solita group is very restricted. So even in the topological level, it should be semi-conjugate to the standard action of x goes to 2x and x goes to x plus 1. This affine action. It is not conjugate, but semi-conjugate. Yeah. It's in the Homeo case. Yeah. Okay, thank you.